Welcome to this lesson on hydrates. The question of the day: what are the properties of salts, or in other words, compounds with ionic bonds? Salts have very high melting points. A lot of the time they like to dissolve in water. When they do, they form electrolytes, which are solutions that can conduct electricity. Ionic compounds or salts form a crystal lattice, and that crystal lattice is an alternating pattern of cations and anions, which are held together by their opposing charges. Now, a hydrate is kind of a type of ionic compound. It is a crystal lattice that has a specific number of water molecules physically stuck to it. I like to think of it as a water molecule. This blue chunk is kind of stuck inside of an ionic jail. It doesn't fall off very easily. You have to put in a decent amount of effort to get that water out of there, but it is possible because it is only physically associated with the water. So because it's only physically associated, you only need a physical change to remove the water from the salt. We can remove that water just by heating it up. It's really that simple. Water is only physically associated with this salt or with this crystal lattice, so you only need the physical change of changing the temperature. You have to just get the water to evaporate. Ionic compounds have exceptionally high melting points. When you heat it up, because the ionic lattice has a very high melting point, there is no concern about the lattice melting. The water will evaporate long before then. It'll evaporate at 373 Kelvin, and most of your ionic lattices are going to melt over 1,000 Kelvin. So we don't have to worry about that. The water evaporates much more quickly and pretty easily. So we have this ionic compound, it's called a hydrate, and we are going to put it over heat. You can put it on a hot plate sometimes even, but most often we'll put it over a Bunsen burner in an evaporating dish a lot of the time. Sometimes we use a smaller version of this that has a lid. It's a little more like cup-shaped as opposed to bowl-shaped, and that's called a crucible. Typically it's ceramic. The ceramic itself gets really hot, which helps to evaporate out the water that's stuck in this hydrate. And when we have dried up all the water, we no longer have a hydrate. It's not hydrated anymore. We now call it an anhydrous salt. Now, practical uses of this, if you have a basement or a closet that has a lot of dampness to it, you might get one of those like anti-dampening things. It's like a plastic cup. It has like these little chunks of, it's usually white, like a really heavy looking salt. Sometimes they like curve them so they're pretty, like a circle. Sometimes they'll color them. Those are the anhydrous salt, and they are going to try to snatch up water. So they'll snatch up water vapor from your basement or your closet and remove dampness. You'll also see these anhydrous salts in the silica gel packets. Those are going to remove moisture from like the inside of a new pair of shoes or inside of a new bag. If you get a new backpack or a new purse, those typically have those silica gel packets in them, and that's going to help to remove any moisture from inside of the bag, especially shoes. When they're in the store and you're trying on shoes that maybe another person tried on, you want all that moisture sucked up and gone. Using the percent by mass equation, we can figure out how many grams of water are going to be removed from a sample when we heat it up, just like this. If we have a certain number of grams here and we know the percent by mass of water, we can figure out what percent of the total is going to be lost when we heat it. So we can know like really exactly how much water an anhydrous salt is able to hold on to. Now, once we have the percent by mass of water in this compound, we can use that ratio to determine exactly how many grams would be lost from our sample, even if our sample is larger or smaller than what the molar mass of this compound is. I'll show you that in a few minutes. We are also going to use this to calculate the percent error when it comes to lab procedures of removing water from these hydrates. Some hydrates are cooler than others. If you are going to do this in your high school chemistry lab, your teacher will probably give you a sample of a blue salt called copper 2 sulfate pentahydrate. And that is going to be blue when it is hydrated, and then it's going to turn to this white, very, very, very pale blue when the water is being removed. So this happens for quite a few hydrates, specifically the ones that contain a transition metal like copper. But not all hydrates have this cool color change. Not most, but a good number of them start out as white salts and then end as white salts. A lot less exciting. Whether we have a color change in our hydrate or not, as we are dehydrating it, typically we're going to be looking for more precision. So what we do is we dry that sample a little bit. We try to get it as dry as we can, and then we'll take it off the heat, give it a break for a minute, let it cool down, and then we will drop that onto a balance. We're going to record that measurement, and then we are going to take it back to the heat and heat it up some more. If your sample has lost mass in between those two measurements, you're going to, put it on to begin with, put it on maybe halfway through, put it on again. The idea is that you want your mass to come out constant, going back and forth between the heat and the balance. If it goes on the heat and you're not losing any more mass, it means that all of your water must be evaporated. So we're going to look for constant mass as we dry these things. Sometimes when you do the lab, you have like how much mass you can lose before you just call it and say that it's dry enough. But typically you're going to have your theoretical amount that should have evaporated to begin with. And you're going to get that from using the chemical formula. Again, I'll show you that in a minute, but we will have like a theoretical number that you should hit, and you should be keeping track of that as you are drying this. That's just to shrink your percent error. If you're anticipating that you're going to dry out 10 grams, but you've only dried out 6 grams, you're going to want to add it back to the heat. But if you have anticipated drying 10 grams and you have actually dried like 9.5 and your mass keeps coming back constant, we could say that that half gram is just error. Not that we want to, but when we have the data of that constant mass coming back over and over again, it kind of helps to reassure us that we've done everything properly. So here we go with an example. What is the percent by mass of water in copper 2 sulfate pentahydrate? Copper 2 sulfate is just the ionic name of this ionic piece. This dot does not mean multiply, it means physically associated with. And here we have 5 water molecules, pentahydrate, physically associated with the copper 2 sulfate. So here we have 5 water molecules physically attached to 1 unit of the copper 2 sulfate. In order to figure this out, we're going to stick to that QMT chart, but there is a tiny little thing here. The copper 2 sulfate contains an oxygen, and so does the water. And we're going to want to keep that separate because as we dry this sample, this oxygen that's part of the copper 2 sulfate is going to stick around. It's going to stay in the evaporating dish. But this oxygen is part of the water and it is going to evaporate. So when we do the QMT chart, we want the copper 2 sulfate all together, and then we want the water all together. And you see I have this extra box here. That is for the total of all of the water. So looking at the chemical formula, we're going to drop in the quantity for each of these atoms: 1 copper, 1 sulfur, 4 oxygens in the ionic piece, 10 hydrogens, and 5 oxygens in the water piece. Next, we're going to hit the periodic table and pull those masses. Again, I'm just going from the whole number, but your teacher may want you to go out to match your periodic table. When we multiply going across, you are going to match the number of significant figures to the mass. In this case, we are getting all of our totals, and we have a separate total here for the water, which is going to be the 10 plus the 80, giving us 90. And that is per the copper 2 sulfate pentahydrate, 90 grams per mole are going to belong to water, and the mole itself is going to come out to 250 grams. To figure out the percent of hydration, or the percent by mass of water, we are going to take the 90 divided by the 250, and we're going to come out to 36%. Meaning, whatever mass we put in the evaporating dish, 36% of it should evaporate because that's what the water is. And now I'm going to show you 2 ways to solve these problems. It's really just going to depend on your preference. I prefer the ratio, but if you like the percent, that works too. We are given an example of 5.2 grams of copper 2 sulfate pentahydrate being heated in a lab setting. And the question is, what is the expected final mass when the sample is totally dehydrated? Looking at the QMT chart you just did, there's 90 grams of water per 250 grams of the hydrate. So we can kind of just set this up. Every time I do a ratio, I talk to myself. I don't know how else to do a ratio. This is just how I do it. 90 grams of water per 250 grams of the hydrate is going to be, I don't know how many grams of the water out of the 5.2 grams of the hydrate. The important thing here is that the water is on the top and the hydrate is on the bottom. You just have to match them going across. It doesn't really matter because we're cross multiplying, but you can't have water on the numerator here and then in the denominator here. You have to do across the top or across the bottom, either way. So this is going to give us a cross multiplication because we have two fractions equal to each other with just one unknown. So we cross multiply and we will get 250x is equal to 468. We're going to divide both sides by the 250 to get x by itself, and we will be left with 1.872 grams of water should evaporate out of our 5.2 gram sample. So the 1.872 grams represents the water, but the question was how much of the anhydrous salt would be left over. So we have to subtract the water from the original sample, which is going to leave us with 3.328 grams of anhydrous salt. Again, I know I'm not really on board with the significant figures here. This is not how you would do it for the sig figs, but this is really just to teach you the hydrates. So we'd have 3.3 grams of the anhydrous salt left over. Now we can look at this in a different way. We can look at it from the percent. This is the exact same question, but the follow through or the procedure is going to be a touch different. So again, we're working with the 5.2 grams of the hydrate and we're heating it. And the question is, what is the expected final mass when totally dehydrated? This is how I was taught to set up my percent questions. We ask ourselves, what is 36% of 5.2? This 36% came from the QMT chart. When we did the 90 divided by the 250, we got 36. I was taught to put vertical lines on the is and the of. Is comes out as equals, of is multiply. What is x? I don't know what it is. The 36% has to be converted to a decimal so we can do math with it, and then the 5.2 is going to stick around. So here we would get x equals 0.36 times 5.2. The answer we get is the same as before, 1.872 grams of water just from doing this calculation. The question was, what is the final mass of the anhydrous salt that's left over? So again, we have to subtract the mass of the water from the original sample, leaving us with 3.328 grams of the anhydrous salt that is left over. Now, depending on the size of your sample and the shape of your evaporating dish, sometimes water can be trapped underneath the crystals and it has a hard time evaporating. So this is why we need to cool the evaporating dish and check the sample every once in a while just to make sure that this water is evaporating properly. A lot of the time, also, when you heat this up in the evaporating dish, the water like rushes to get out, and sometimes it'll like kind of pop like popcorn. The water rushes so quickly that it's able to push the salt, and it'll pop like popcorn, and it's hot. So a lot of the time with the crucible, we'll put the crucible lid on the top, but leave it a little ajar so that the steam can come out. In an evaporating dish, you kind of want it to be big so that the water can escape quite easily. You kind of want your sample sort of thin. There's a lot of technique to it, and people have different preferences one over the other. But for this reason of the water becoming trapped, it's important to take that break, let the dish cool a little bit, and put it on the balance just to see your progress. Again, once you've done this a few times and you come out to a constant mass, then you can assume that you've dried your sample as much as you really can. Sometimes water just gets stuck. It's just the way that it is. Also, these hydrates are physically associated with the ionic compound. So sometimes, especially when your sample is a little bit older, depending on the conditions of the lab room or like the state of the bottle. If you do a lab and it's left open in a dry room, sometimes the water will just evaporate on its own. So you don't always start out with a perfect uniform hydrate. I mean, usually you do, but not always. So that's also something to consider when you do your percent error calculations. As a reminder, your percent error calculations are going to be your experimental data minus the accepted data divided by the accepted data times 100. So for copper 2 sulfate pentahydrate, your accepted value would be 36%, and your experimental is going to be derived, of course, from your specific data. Sometimes it's more, sometimes it's less. The top should be an absolute value, meaning it always comes out positive, and your experimental results are considered valid when your final answer comes within 5%. Now, throughout this whole lesson, I've been referring to copper 2 sulfate pentahydrate, but how do you name these things? So I kind of alluded to this before. The ionic part, you're just going to name it following your regular ionic naming rules. You are also going to name the number of water molecules using a covalent prefix. So this is stuff you should already know. It's just rearranging it a little bit. As far as I can remember, this is the only time you'll mix ionic and covalent naming. So the ionic part, name it ionically. The number of water molecules will get a covalent prefix, and then you're just going to tack hydrate on the end. So here is some practice for you. I would pause the video and make sure that you know how to do this. You should not only name them, but you should figure out the percent by mass of water for each of these compounds. All right, here we are. This is calcium sulfate hexahydrate because there's 6 waters. And if you follow through with the QMT chart, keeping your water molecules separate from the ionic piece, you should come out to this being 44% water. Now, if you were to dehydrate this in the lab and your data told you that you evaporated 40%, then you would do your percent error with 40% as your experimental and 44% as your accepted. This would also be your theoretical amount that should evaporate, which is going to help guide really how long you need to heat your hydrate and how close you are to that final answer. All right, I moved my bubble so you could see the bottom of this slide to get more answers. Remember, the prefix for 10 is deca, 7 is hepta, and 2 is di, not bi. If you have any questions, please leave them in the comment section below the video. I'd be happy to answer them for you. Subscribe so you don't miss the next lesson. I can't wait to see you there. Bye.